Hello everyone. In this lecture video, I am going to be talking about aqueous solutions. Aqueous solutions is basically just means to say it's solids or liquids dissolved in water. Aqueous basically means water. Aqua is Latin for water in this case. There are two general types of aqueous solutions. That is when a solid, which is called the solute, is dissolved in water. And the solid has to be either an ionic compound, and if it's an ionic compound, that solid must follow solubility rules. And I'm just gonna exit this very quickly and show you where those solubility rules are again. It's in page 7 of your exam reference sheet. So again, in order for an ionic compound or an ionic solid to be soluble in water, it has to follow this rule. So anything that has sodium, potassium, and lithium in front is soluble in water. Okay. Halides are normally soluble, so sodium chloride, sodium bromide, but if the positive ion is silver, lead, or mercury, then that ionic compound is not soluble in water. So again, in order for you to determine whether an ionic solid is soluble in water, you have to use the solubility rules, which is in page 7 of your exam reference sheet. Having said that, there are also, in this case, covalent solids that are soluble in water, and the dominant example of a covalent solid that's soluble in water are sugars. Okay, so fructose, sucrose, okay, lactose, galactose, glucose. All right, so sugars, simple sugars predominantly speaking, are generally soluble in water. Okay. Then the other type of an aqueous solution is when you actually dissolve a liquid, also called the solute in this case, in water. So again, the solvent in both cases of, again, us name aqueous solutions, the solvent in both cases is water. Okay, it has to be a polar liquid in order for it to be dissolved in water. Non-polar liquids do not dissolve in water. We know this because an example of a non-polar liquid is oil, vegetable oil. Okay, so we know for a fact that if you dissolve a vegetable oil in water, you will separate into two different phases, with the non-polar liquid, the vegetable oil on top, and the water on the bottom. Okay, so again, two different types of aqueous solutions, and aqueous means anything dissolved in water. Example, so sodium chloride is soluble in water, so therefore sodium chloride in water is an aqueous solution, right? Silver hydroxide, however, is insoluble in water. This is again in page 7 of your exam reference sheet. So therefore silver hydroxide in water is not an aqueous solution, right? Ammonia, which is a polar liquid, is miscible. Miscible means it mixes with water, so therefore ammonia in water is an aqueous solution. C8H18 is octane. Octane is the stuff that you put in your gas tank. Okay, it doesn't mix with water, so therefore octane is not an aqueous solution. And maybe I should go back here. Now we need to understand again that in aqueous solutions, solids have to be, in this case, has to be able to dissolve in water, following the solubility rules for ionic solids. And it has to be a polar solid, like in this case, sugars. In order for a liquid to be dissolved in water, it has to be a polar liquid. And again, I hope that you remember how to determine the polarity of a molecule from the very, very beginning parts of this semester. All right. Now, how do aqueous solutions actually form? So here we have potassium chromate, right? Which is, and here we have pure water. We put potassium chromate, or dichromate in this case, in water, and as we can see, this is actually a sign that a aqueous solution has actually formed. The orange color from the potassium chromate actually is spread out in the whole solution, so every single portion of the solution will be uniform in color. There is not going to be one region which is going to be darker and the region that's going to be lighter. And that is an example of an aqueous solution. In order for it to be considered an aqueous solution, it has to be homogeneous. All right? Homogeneous means that if you take any, and if you test any part of the solution the solute and water ratio is going to be the same, right? Which brings us to a very, very important point. You can keep adding potassium chromate and it can keep appearing like a homogeneous solution, but there is still a maximum threshold for a solid to be dissolved in water. Eventually, like if we have ever put too much sugar in our coffee, if you put too much sugar in coffee, sugar is obviously dissolved, in this case soluble in water, but if you put too much sugar in your coffee, it eventually settles in the bottom. At that point, it's no longer insoluble. It's no longer soluble, which means it's going to be considered insoluble. Okay, so again, it has to be homogeneous. So that's again a very, very important key. If I throw something in there and it settles in the bottom, okay, what that means to say is you're gonna have an area which has less solute, and you're gonna have an area, obviously the bottom, which is more solute. That is an example of a heterogeneous mixture, which means to say that the components or the ratio between, in this case, the solvent water and the solute, the solid, is not the same at all the particular areas of the solution. Okay? So this is an example of why things actually dissolve in water. So if you recall previously, ionic compounds are the combination of a positively charged metal ion and a negatively charged, in this case, non-metal ion. Okay, it could also be a combination of two polyatomic ions. What happens is, since chlorine in this case has a negative charge and since potassium has a positive charge, they attract different parts of water molecules which have a dipole moment. Recall that in a water molecule, the hydrogen has a partial positive charge and the oxygen has a partial negative charge. Okay, and that is one of the reasons why potassium chloride in water actually splits apart. It's because the interaction between the potassium and the chloride ions are actually replaced by the interactions of chlorine, in this case with partial positive hydrogen portions of the water molecule, and by the partial negative oxygen of the water molecule interacting with the positive potassium ions. So it's just, you're just replacing the positive negative interactions of these two ions by the positive negative interactions between portions of the water molecule and the individual ions in this case. All right? This is also one of the reasons why there are some ionic solids, actually a lot of ionic solids, that are not soluble in water. And the reason why is the interaction between the positive ion and the negative ion is so strong that no amount of water molecule will be able to break them apart. Okay, this is actually why some ionic solids are actually not soluble in water. And FYI, right, this is just for your information, you don't need to memorize this. Every single solid, ionic or otherwise, is actually partially soluble in water, which means to say if you put just a very, very small amount, it actually dissolves in water. Okay, but for purposes of solubility, the actual threshold is a 0.1 molar solution. Okay, has to be completely homogeneous, right? And we're going to talk about molarities pretty soon. So in this case, solids or liquids that are soluble in water can also be divided into this thing called electrolytes or non-electrolytes. So sugar, or in this case, in this example, ethanol. Ethanol is in this case is CH3. It's this weird molecule that we have covered before already. CH3, CH2OH. It's the thing that it's in that's very, very well loved in Wisconsin. It's called drinking alcohol. Okay, so ethanol, folks, as you can see, does not split apart into individual components in water. So ethanol in water remains as one unit, similar to what I've talked about previously. Okay, so what happens is in solution, in water solution, since there's no whole positive or whole negative charge, a current cannot be conducted in a water solution. And this is actually what, this is actually, we actually have this machine in the laboratory, and maybe we can actually go through a couple of solutions that actually has electrolytes or non-electrolytes. However, potassium chloride, which separates into their positive and negative components, actually conducts electricity. And why is that? Because what electricity actually is actually the flow of electrons, or the flow of ions in this case. So if you put a negative and positive poles in a solution that is high in potassium chloride, the negative ions then migrate towards the positive side, and the positive ions then migrate towards the negative side. And that is actually what a current is. It's just the movement of ions to their opposite, in this case to whatever poles they're actually attracted to. Again, negative is attracted to the positive pole, okay, which is called the cathode, and then the positive ions are actually attracted to the negative pole, which is called the anode, predominantly speaking. All right. In some cases, this is a high conductivity. There are actually some instances in which you actually have low, you still have conductivity, but partially. And then this is the case in which it's going to be about acids and bases. And we're going to be talking about acids and bases again at the tail end of the semester. So we can save this, in this case, this discussion at this point. So again, electrolytes are in this case are particles that actually divide into positive and negative ions in water in an aqueous solution, and therefore they conduct electricity. All right. So solubility is also affected by temperature. All right. So what this means to say is that if you have ever done this, I don't know if you've ever done this before, and you can try this at home, what happens is if you put, let's say, 10 tablespoons of sugar in a liter of water, eventually what happens is all of that sugar, this is actually sugar here, folks, okay, C12H22O11, just table sugar, okay. What happens is there will be a point in time in which the solution will actually have solids in the bottom. All right. So at that point, this term is actually called supersaturated. All right. What happens, however, is if you heat, this is my, in this case, my drawing of a heat. That's a terrible drawing. What happens, folks, is the sugar that was not easily dissolved in water when it was colder, actually in this case disappears, and I should have used a different one. All right, and the reason why that is it has something to do about intermolecular forces, right? So when it's cold, you have to understand about cold, particles, all right, especially solids, tend to not have a lot of kinetic energy and tend to have closer distances between each other. However, as you raise the temperature of a system in which there are solids, what happens then is the kinetic energy between the solid particles increases to the point in which they overcome the intermolecular forces that forces them to be closely together. And so this is one of the reasons why, in this case, solids, when you heat them, they actually then in this case disappear. Just think about it. If you burn a piece of wood, do you still see wood at the end? No. Wood disappeared. Why? Because the particles of wood that was solid before, when it wasn't burning, the distances between the particles are actually dispersed in such great distances that they have turned into the gas phase. And obviously you cannot see gas particles. Okay? So this is something to do with this. And we are going to talk about a few instances here. So let me just give you a couple of examples here. Let's see. Let's look at something that actually crosses the line solidly here. Okay, so let's look at sugar. Okay, or maybe let's look at sodium bromide. Sodium bromide at 20 degrees Celsius, which is around room temperature. At 20 degrees Celsius, the amount of sodium bromide that can be dissolved in 100 grams of water, that's 100 mils, folks, is around, that's actually a high amount, is actually around 120 grams. So you can actually put 120 grams of solid sodium bromide in 100 grams of water with no settling on the bottom. At that point, that's called saturated. Anything below that number, 110, 60, is unsaturated, and anything above that level is called super saturated.